So now that we're done with the prerequisites, let's get on to some actual physics content, starting off with units. So this is a very, 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 very important part in physics. Often people tend to overlook this entire topic because they find it boring, quote unquote, but actually it is incredibly important to note. So a standardized quantity used to express a physical measurement such as length, mass, time, or temperature, etc., is referred to as a unit. Regardless of the measurement system used, these units serve as a common language for scientists and engineers to communicate measurements and data for a standardized and consistent manner. So that is quite a wordy sentence, but basically what it means is that every country, bar the United States at this point, because they refuse to change, have standardized what a meter should be. We'll get onto what that is, but simply put, if somebody was to make a beam, say a metal beam, now obviously it's not going to be red, hopefully. So let's say they make a metal beam, and they say it's 2 meters long. And say this originated in, let's say Brazil. So let's say a Brazilian company makes a 2 meter long rod. If they ship this 2 meter long rod over to New Zealand, the people in New Zealand will also be able to verify that yes, this is a 2 meter long rod, because we all use the same measurements. And of course, if Brazil's measurements are screwed and New Zealand's measurements are screwed, they will probably go to a third party and get their measurements in case their units are slightly off, but it's pretty much negligible at the scale of 2 meters. So the system that we use is called the metric system. So you have the meter, kilogram, and the Kelvin. Now the key with the Kelvin being the SI unit and not the Celsius is for a very important reason. The properties of the metric system is that no metric unit is meant to be below 0. So the coldest possible temperature is defined at 0 Kelvin, which is around minus 273 degrees Celsius. I don't know the conversion in Fahrenheit. I believe it's minus 450 something, but I wouldn't be so certain. So the imperial system is obviously disregarded because it does leave a lot of error in calculations and there's just so many of them, so it makes conversions really, really wonky. So here's a comparison of metric and imperial. So the metric unit's 1,000 meters in a kilometer, 1,000 grams in a kilogram, 100 centimeters in a meter, and 1,000 mils in a liter. The imperial equivalent, 1,760 yards in a mile, 16 ounces in a pound, 12 inches in a foot, 128 fluid ounces in a gallon. It's all just too much. You might argue that it's sort of convenient because there's powers of 2 here, but that there really isn't. The powers of 2 make no difference whatsoever. So here's a case study to showcase the importance of units. Now this is very wordy, but it is going to be the last thing we do in this video, so you can skip on to the next video if you wish, or you can listen to this story. So the Mars Climate Orbiter is a space probe designed to study Mars' climate and atmosphere. It was launched in '98 as part of a mission to explore Mars, but it was unable to complete its mission due to a fatal error related to unit consistency. So unit consistency is making sure that all your units are the same. That's a pretty apt name for it. The issue arose because different project teams used different units of measurement to communicate with one another. NASA, for example, used the metric system, which is meters, kilograms, seconds, whereas Lockheed Martin, which is another aerospace manufacturer, used feet, pounds, and seconds. Now, of course, the imperial system doesn't have its own unit of seconds, but the shortened version of these, so the metric system is often called the MKS, for meters, kilograms, seconds, and the imperial system is FPS for foot, pound, second. So during the development of the spacecraft, this discrepancy went unnoticed, and the software used to control the thrusters was not programmed to convert between the systems. Because why should it? It's so unnecessary to waste programming space in converting units because Lockheed Martin was too lazy to change. So as a result, the thrusters on the spacecraft fired too early and for too long as it approached Mars, which caused the spacecraft to enter the atmosphere at an incorrect angle, resulting in the loss. So it essentially burned up in the atmosphere. The failure of the Mars Climate Orbiter emphasizes the importance of using units consistently in scientific and engineering projects, It serves as a warning for future missions, emphasizing the importance of meticulous attention to detail and standardization in aspects of... Okay, that's just pretty much me waffling there. But if you want to look at another example of consistency for units, I recommend looking at this thing called the Gimli glider, Gimli glider. It was an aviation incident that happened because refuelers at a Canadian airport, as far as I remember, got confused with the units for liquid capacity and filled it up with about half as much fuel as it needed for the whole trip. Luckily, no one was injured and the plane landed safely.